Good afternoon, everybody. Thanks for everyone for coming. We're here today to present the final part for our senior design capstone project, UGarden. So just a quick and brief outline what we're going to be doing. We're just going to introduce ourselves, talk about our motivations, talk about the project a little bit as an overview, go through some system requirements and what we felt was important for the project, talk about some key module components of our project, talk about the testing and the results that we got from our testing, and we're going to do some listing the cost analysis, and then we're going to end with our future work, any plans that we might have had for the future. So to start off, my name's Nick, and I'm the team leader, and I'm part of the hardware team.
I'm Alec, I'm the hardware leader.
My name is Shabeli, and I'm the software leader.
I'm Tanvir, and I'm part of the software team.
So for our motivation, we actually had one of our group members who went away on vacation and their garden died because there was no one to water it. So from this, we realized that people need a way to remotely monitor and care for their gardens and properly maintain them while they're away from home. Our product is going to benefit those who need to maintain their garden remotely, especially if they don't have the time or the physical capability to maintain their garden. So our description, we created an automated system that's going to water and monitor the garden using multiple sensors, temperature, humidity, soil moisture, light. Each sensor is connected to the microcontroller, which in our case is a Raspberry Pi, and it will communicate wirelessly to a web page. The watering system depends on moisture levels to decide when to begin watering. Temperature and humidity data determines how long to water. The web page monitors garden status even while the user is away from home. So societal impact. Every garden can make a little difference no matter how large or small they are. So plants overall reduce pollution by decreasing the amount of carbon dioxide in the air. If your garden has edible plants, it means you don't have to shop at the supermarket for them, and you can cut down on your energy footprint. Plants also help remove chemicals and bacteria from groundwater, as well as providing a food source and home for wildlife. Trees and plants also absorb sound, which can help with noise pollution. Vertical farming is also becoming more popular in urban environments. Local indoor operations have been cut down on transportation costs and land use.
So we're going to talk about our system requirements and our needs identification. The system is powered by a battery, which is charged by a solar panel. The web page that we have will display soil moisture, temperature, humidity, and light levels. And our watering system waters each quadrant individually. It automatically waters when the soil moisture levels are not adequate, and then the watering time is dependent on soil moisture and humidity. Our production cost should not exceed $250. So as far as our competition, there are some do-it-yourself solutions. One of them is GardenBot, and that's an open source project that allows a user to automatically water a garden through separate modules that they can build. The problem with this is that it lacks wireless communication and ease of use. Then there's Parrot Flower Power. That's discontinued. That used Bluetooth to communicate with a mobile app. That lacked long-range communication and the watering system. And finally, there was PlantLink, and that is a wireless soil moisture sensor with an app, but it didn't have the watering system.
So market issues with the previous products. There was a lack of integration of sensors. Very few. They only had one sensor as opposed to the three that we have. And the sensor only showed data to the user but didn't actually use it for anything. Like our sensor data will be used for watering the system. The products also only offered qualitative measurements instead of quantitative measurements, so you only got a feel for the data. You couldn't actually do anything with them. And they weren't a full system, so like I said before, they didn't use the data to automatically trigger watering. And they also had unreliable connection because they used Bluetooth, which had a very limited range as opposed to Wi-Fi. So the user had to be near their garden to monitor anyways, in which case you wouldn't even need the product. Customer needs identification. We wanted our product to automatically water the garden depending on the moisture levels, soil moisture levels. Watering time will be dependent on the gathered temperature and humidity data. We wanted it to be easy to use for the user, so it has very limited controls, and all of the data is displayed on a user interface on a website quantitatively. And we wanted them to be able to monitor no matter where they are, so we used Wi-Fi instead of Bluetooth. And this is our objective tree. For the previous slide, we have functionality, ease of use, and wireless communication.
Now we're going to talk about the key modules of our project. So this is an overview of the hardware. We have the garden bed and then the piping system that runs through it. There are 4 branches off of the piping system, and the branch has a valve, a nozzle, and then a cap at the end.
So this is our physical software diagram. We start off with the Raspberry Pi, which is connected to all of the sensors. Every 2 minutes, the Raspberry Pi will send a trigger to the sensors to collect data from it, and it'll organize that data into a CSV file. Every 10 minutes, the Raspberry Pi will use a secure copy protocol to send that file over to our Amazon web server, which is running a Mongo database and Node.js service. Once the file is copied over to the server, it'll open up a Mongo command shell where we use curl to transfer the 5 most recent pieces of data onto the web page, which is on port 3001, and the user will be able to view the web page on their browser, and it'll show the most recent pull along with the 5 pieces of data in chart form. And this is our MCU functional decomposition. We have the Raspberry Pi Zero, which is our microcontroller. It is connected to 4 solenoid valves using our GPIO pins. And over here is our temperature humidity sensor, our light sensor, and an ADC, which our soil moisture sensor is connected to, and the top 2 and the bottom are connected through I2C.
So over here we have an overview. It's functional decomposition. I think the highlight of this part is the solar panel controller. It interfaces the panels, the DC source, the battery that we have, and the DC to DC converter. The DC to DC converter, it powers the Pi while getting 12 volts from the panel controller, and the panel controller sends 12 volt signals to the valve circuit, which ultimately turns the valves on and off. So our testing plan composed of 3 parts: unit testing, integration tests, and
Can
the
you use the microphone a little, please? Could you speak in the microphone a little?
So the unit tests composed of tests that, sorry, I lost my train of thought. Unit tests, the sensors, the valves, and the database and the website are all individually tested. So we created testing procedures for the sensors, for the temperature humidity sensor, the soil moisture sensor, and the light sensors. We tested them individually and then all together. We tested the website locally and then on the AWS server. The integration tests, everything was put together. The hardware and the software were put together, and that was tested at one time, and then the acceptance test would be just testing it in the environment which the customer would use it.
This is our testing results. So for the valves test, we wanted to write a program that would cause 1 valve to open at a time. And that program, we made that successfully. And then the second part was to actually run the program with the nozzles connected and controlling the valves that way. And that was also a success.
So for the temperature and humidity sensor, we actually had to conduct some experiments where we used sodium hydroxide and sodium chloride, both aqueous solutions, contained in small jars, and we test for equilibrium humidity at the existing room temperature. And the reason we use these 2 compounds is because they're easy to find, prepare, and have fairly constant humidity equilibrium at room temperature. And as you can see below, from the data we gathered, we had a relatively low percent error.
And so this is the test for our light sensor. To test the light sensor, we performed experiments in environmental conditions that we expect the sensor to be exposed to. And so we chose the 4 conditions: indoors, overcast, under shade in a sunny day, and direct sunlight in a sunny day. We used weather forecasts to plan for the date and time to perform the experiments. And our second row here are the accepted ranges for light intensity under these conditions. And the third row is our measured average. We don't have a percent error here because light intensity is such a huge range that our goal was just to make sure that all of our measurements fall into it instead of a specific value.
So this is the result of our soil moisture test, and what we did for this is we got different cups of soil with different with different amounts of water in them. So as you can see, the percent was pretty low for this too.
So the moving on to the database and the web page tests. First, we used our team used a command line tool called curl. It records. Well, it inserts records into the database that we have. We named it UGarden. We verified each record was there in the database just by using the Mongo shell. After the tests were performed locally on a computer, we migrated the Mongo database onto the AWS server, the Amazon web server, and we did the same process over there. Concerning the Pi to communicating with the AWS server, it SSH'd into it and ultimately SCP'd the CSV file into the AWS server, and we just made sure that the content from the CSV file transferred was there. The web page has two GET requests. They're called GET recent chart data and GET high chart data. They were just verified locally and then using them on the Amazon web server. So moving on to the integration tests, this is just checking the interaction between all the elements, the hardware, the software, so that includes the sensors, the valves, the PVC pipes, and the software elements, the AWS server, the MongoDB, and the Node.js server. So first we integrated the Pi and the sensors with the existing PVC pipes that we had, and that went well. It was fully integrated and we had no problems with that. We then ran tests to ensure the Pi would trigger the valves at certain conditions. So the conditions were if that watering would begin at below a soil moisture content below 25%, and temperature then determined how long you would water for. So if it was less than 30 degrees Celsius, it would just be watering for 3 minutes, and if it was greater than that, it would be running for twice the amount of time. And finally, we just made sure that the collected data from the sensors was being transferred over to the AWS server, and we checked that out by querying the Mongo database, and that went fine too.
So for the acceptance test, we checked the system under the conditions that the consumer would receive the system. So the only consumer-oriented aspect of our project would be the web page. So the consumer is able to visit the web page, and that web page would display the current sensor readings as well as a graph of the data. This test was successful.
Here's a bit. Well, on the left is a picture of our setup. We have the solar panels, the batteries, the charge controller, everything in that little box with all of our electronics. And then on the right is a video demonstration of our piping system.
Here is a preview of our web page. This is what the user would be seeing. It shows you the most recent pull from the sensor data, which consists of the date, time, the temperature, the humidity in a percentage, soil moisture levels, and the light UV index. And below that is a chart of the 5 most recent data points. So this was our projected timeline for the first semester of senior design. We began with a month of research, which consisted of what kind of sensors we would need, how we needed to put things together, what we needed for building the system, followed by the hardware team doing circuit and hardware design, and the software team working on integrating the sensors with the microcontroller. And we met our milestone for the end of the semester, which was to have a prototype of the system, of the hardware side of the system built, and for all of the sensors to be tested with the microcontroller individually. For the second semester, we made improvements on the hardware side and on the software side. We continued working on the software and making sure that everything was executing properly, and then we moved on to user application, which was the web page through the Amazon Web Services. And then in the final stages, we worked on integrating everything together and then running it through tests to make sure that it worked as intended. And that was our final milestone, which we achieved.
This is our bill of materials. Our total cost came to $309. The reason it was over budget was because certain things were more expensive than we thought they would be, and we needed more things than we thought we would. So that's why it came over budget.
So for our standards, we actually added 2 new standards since the last time we presented, the SSH and SCP standards, as well as the JavaScript object notation, JSON. For future work, so in order to make our product even more appealing to a consumer, we would like to implement having the user be able to request watering commands, so they can request when they would want the garden to water. We would also like to create a mobile application that can receive the sensor data and send user requested watering commands to the Raspberry Pi. In addition to this, we would also like to be able to monitor and show the user data on their water consumption, and also implement a water leak detection system. And these are our references.
And I just want to give special thanks to 2 of my colleagues and closest childhood friends, Frank and Alex. Frank graduated last year from Maritime with a degree in mechanical engineering, and Alex on the right, he graduated also last year from Marist with a degree in computer science. And I'd just like to end if anyone has any questions. Let's go ahead.
Hi, I saw in your picture you were delivering the water, and I like your system. It's quite interesting. But the water distribution system looks rather, I'm surprised you have it so high off the ground. That would be strongly affected by wind conditions. You might not be able to deliver the water that you think. Why didn't you put that right down on the ground? It's much more efficient distribution.
Definitely. So in the in a consumer setting, somebody would probably just put this straight into the ground. I made the legs long. Okay, they're probably it probably sits about this high. Someone would probably put this about 8 to 12 inches into the ground. That would definitely make it much more stable. In the interest of time, I just didn't want to drill the holes. So considering that, we could have done the test, probably just putting it into the.
Well, even if you just cut it in a half or a third, would that be improve things?
It would. I just didn't have the tools at the moment, but yes, it definitely would have improved.
Well, that would definitely make it a much more usable system, right?
Yeah, it definitely would.
Very good. Thank you. Very nice.
Sure.
Have you done any gardening?
Yes, my family personally has their own garden.
I hear that how often do you check the moisture or dryness of the soil and stuff? How
Not very often. So typically, someone could probably check the moisture of your garden probably like 2-3 times a day. It's not every hour is a little excessive.
I was a little bit thrown off. Somebody mentioned something like 10 every 10 minutes.
Yeah. So it would collect sensor data every 2 minutes, send it over to the server every 10 minutes, and then it wouldn't actually it wouldn't do anything unless it needed to be done. But it was just constantly reading the data.
In the interest of the test and interest of time, we performed the test a couple of days ago. We wanted to collect the sensor data within a reasonable amount. We didn't want to wait around in my house for 4 hours. Someone have a question in the back? I can't see too well. Go ahead.
So is there an implementation for flowers that take more water than others, and do you have to place those flowers somewhere far away from other ones, sort of like manage your placement of where you want to put things?
So the type of plant being watered isn't dependent. Let me rephrase. Watering and the data you collect isn't dependent on the type of plants you're planting or you're growing. It's totally independent. All plants need water. Some plants need different amounts of water than others. We would probably consider that into future work if we wanted to develop this project even further. I mean, I know that there are certain systems that have certain, there are certain products that are trying to get onto the market that have an entire database, an extensive database of different plants and how much they're watered and what kind of nutrients they need. in the interest of a senior capstone design project of a 10-month span, it's definitely a high mark. We would probably do that in 3 years, but yes, it could definitely be considered. That's it.
Okay, thank you.
Very good.